determinant, determinants, and what else? And the multilinear functions. Okay, so the first thing I would like to talk about is indeed the concept of a multilinear function. And well, for that, what I would like to remind you, well, first of all, before talking about multilinear something, right? Let's recall what is a linear is, what linear function is. Well, by linear function, well, one usually means, or say linear transformation, linear function. So it's a function from where to where. So it's a function from the, say, vector space, some vector space V. So V is a vector space. And well, so, right, so V is a vector space, and we would like to deal with a function from V to F. Okay, and well, this function should satisfy the standard properties of a linear operator, namely, whenever I have a sum of two vectors, it's the same as the sum of values. And so whenever I have a scalar multiple of a vector, it's just a scalar multiple of the respective value. Yeah? So in other words, what's a linear function? Well, a linear function is a linear transformation, right? Linear transformation from where to where? From the vector space V to the field F. So vector space V is of course considered over the field F, to the field F, which one also may consider as a one-dimensional vector space over F. So indeed, a linear function is just a particular example of a linear transformation, right? From the vector space of an arbitrary dimension to the vector space of dimension 1. Okay. So, well, let me yes, exactly. So right. So so let me also add that of course you can look at the set of all such linear functions, right? And of course it has a structure of the vector space because we can add functions and multiply functions by scalar, and this gives us the so-called dual space, right? So let me remind you that the dual space is just the vector space of all functions like this. So this is a dual space. Just a remark. So we have seen it before indeed. So what I would like really to do, I would like to look at the following example. Well, I would like actually to extend it in some sense. Right, so instead of just one vector space V, I would like to put here several many of them. So what do I mean by this? So now let's talk about multilinear function. Well, so basically we would like, instead of V, take several many copies of V. So I can take, of course, what I can do, I can just take, well, suppose that V is finite dimensional. Suppose that V is finite dimensional for simplicity. So I can just take Cartesian product of all several many copies of V. I don't know, say M copies. Okay, and we all know that whenever you take a copies of a vector, well, just take product of several vector spaces, right? Finite dimensional vector spaces. They're the same as direct sums, right? Or if you wish, you can also think about each vector in this product as a tuple of vectors, right? Where each coordinate is a vector in the respective vector. Okay. So this is just a product. Let me take a, yeah. So it's a product or a direct sum. So let me product, direct sum of vector spaces. And well, we would like to have a map F from several many copies of V to F again. And what we would like to require from this map F is that it's linear, it satisfies the same properties, like here, for each copy of V. Okay, so for instance, well, let me just maybe mention, okay, so for instance, what's a typical element of this product? Well, the typical element of this product would be just a M tuple of vectors, right? Vm. So this is V1 is in here, V2 is in there, V3 is in there, and so on, Vm is in there. And by saying that this function f is multilinear, I just mean that, well, I have these properties. Well, these properties, they have to be satisfied for each of the coordinates. Okay, so namely, well, let me write it. So this is, okay, so we have such a function, and we have this property, say v1. I just pick up, say, vector vj, vi, ith vector, and then vi prime. So this is the ith coordinate. And then this has to be the same as f v1, vi, vm plus f of v1, vi prime, vm. Right? So it's like this property, which you just apply to the ith coordinate, to the ith vector. So you see, I just have a sum at the ith position, and I just expand it, right, using this. And the similar for the scalar multiplication. So the similar one for the scalar multiplication. Say if I multiply the ith vector by c, then I can again expand it. So it's c times f v1 vi vm. Okay, so and since these properties of a linear transformation of a linear function holds for each of the coordinates, right? Well, it makes sense to call such a function a multilinear function. So that's what a multilinear function is. Okay, and why would we like to look at such a function? Because there's a very important example of such a function, and that's what I'm going to talk about now. So indeed, the reason why we want to study multilinear functions is because the determinant of a matrix, that you have seen many times in the first year linear algebra, provides an example of a multilinear function, and it's a very important example. Okay, so let me now talk about determinants. So again, whenever I talk about determinants, well, have in mind that, so this is an important example of a multilinear function. Okay, so right, so basically, well, let me come back to this slide and, well, observe that here. Okay, so we take a vector space F, or vector space V, right? So we have taken many copies of the vector space V. Yes. But we can take a very particular vector space in this example. Namely, what we can take V to be just F, well, just a standard vector space, like say of dimension n. So it's Fn. Okay, and so take again n copies instead of m copies here. Instead of n copies, I just take the same number n copies. Take n copies of V. So in this case, what do we have? Well, what we'll have Fn times Fn, right? And that's n times, clearly, right? And what's this? Well, this is a vector space, right? It's a product of spaces Fn. But on the other side, well, we can also write it down as a table, right? As a matrix of the size n by n. So indeed, one can identify these matrices as n by n matrices. Yes. Say, for instance, columns are just, each column is just this vector, right? And rows are just coordinates in Fn of each of the column vector, right? Okay. So, good. So now, well, of course, it makes sense to look at, well, we should assume that n is greater or equal than 2, because otherwise everything becomes too simple, right? And well, so whenever we pick up a vector from the product of n copies of V, we may think that we just take the respective matrix, the square matrix, you know, n by n matrix. So again, I mean, a vector in this vector space is nothing else but just a square matrix A. Okay. Just for just a notational thing. So suppose we have a matrix, we take a matrix A, so A11, A1n, AN1, ANn, okay? And well, we would like to use the following notation, Aij tilde, for the n-1 by n-1 matrix obtained by removing, say, what I do, I just pick up the ith row of the matrix A, I pick up the jth column of the matrix A, and then I just remove them. Okay? The remaining matrix will be denoted by A tilde Ij. So it's a matrix obtained by removing ith row and jth column, and the jth column. So of course it will be one size smaller, right? Okay. So now what I'm going to do, so again, I mean, we started with multilinear functions, and I said that the determinant provides an example of such a function, right? And so now what I'm going to do, I'm going to pick up a particular function, a very explicit function, just going to define it in a minute. And this will be our example. So this will be, we will show later on that this is indeed gives us the determinant. Okay, but the function is just, so definition, define a function, well, we don't know yet whether it's multilinear or not, we are going to check it in a minute, but we'll define a function delta from where to where. So it has to be from this product or from matrices and F to the field F as follows. So again, for n equals 1, everything is very easy. For n equals 1, we just set, well, in that case, delta, in that case, these matrices are just 1 by 1 matrices, right? So this is just the field F itself. So again, this is very easy and straightforward. So we just set this, this delta to be just the identity function So let me put, so there's only one vector, right? So V, well, indeed it's just a scalar, right? A, just a scalar A, right? So this matrix is just A11, yeah. So that's my A, so just a scalar. So set just delta of A11 to be the same. Or in other words, to say this is just the identical function. Again, for n equals 1, we just set delta to be the identical function, nothing else. Now, of course, the interesting case appears when n is greater or equal than 2. In this case, what we do, we define delta of the matrix A, of this vector, right? This multi-vector. Yes, well, we use the following inductive formula. So indeed, we define delta of this matrix in terms of the smaller matrices, in terms of these tilde matrices. So namely, we just set it to be the sum, where J runs from 1 to n. So indeed, we just look at the columns, and then we take this minus 1 to the power 1 plus J. And then, as I promised, this is an inductive formula. So assuming that we know how delta is defined for matrices of size smaller than n, we can define it for the size n, and that's what we do. I mean, we just set it to be the previous size. Okay, so it's this one, A tilde 1J, and then we need still to multiply by the A1J. So what is A1J? We just take the first row of the matrix A and just go by the first row, okay? So that's a formula. So this is an inductive formula again. So you see, in order to compute this value, you need to know the previous ones, right? However, we can always start with 1. Then we can compute it for 2 and so on, right? Okay. Let me just show you how it works, how this definition works. Let me show how this, say, for n equals 2. How does this formula look like? Well, if I just take a matrix A, B, C, D, or if you wish, well, it's better maybe to write it's A11, A12, A21, A22. Then, by the very definition, you see the sum runs from 1 to n. So there are 2 summands only, right? So the very first one, it's minus 1. 1 plus j, so j is 1 in this case, so it's 2. And delta of what? Of A tilde, or let me first write it, 1, 1 times A11 plus, and then there's a second sum at minus 1 to the power 3. Because 1 plus j is 2, right? So that's my j. J is a column, so it's 1, 2. And then I have to multiply by delta of A tilde of 1, 2 times A12, right? Now I can simplify it a little bit. What do I get? Well, I get, look, I mean, minus 1 square is just 1, right? The sign is killed. So I have what? Delta of A tilde 1, 1 times A11. And then minus 1 to the power 3 is minus 1. So it's minus, it gives me minus of the delta of A tilde 1, 2 times A12, right? Now, what are those matrices? Well, of course, this is my matrix A, which is A11, A12, A21, A22, right? Then how do I get, say, A11 tilde? Well, basically what I have to do, I just need to remove the first row and the first column, right, of this matrix. So I just need to remove the first row and the first column, and what do I get? A22. And well, as for A12, what do I get? Well, I have to remove the first row, this one, and the second column, right? And the second column. So what do I get? I get clearly A21. Now, what's the answer then? Well, the answer is then, well, this is just A22, delta of A11, A22, because remember, if n equals 1, that was just chosen to be the identical, right? So just the same scalar. So this is just A22 times A11 minus here's A21, A12. And well, indeed, from this formula, you can actually recognize that this function delta is nothing else but the determinant function of a 2 by 2 matrix. So for n equals 2, delta coincide with the determinant of A, right? Coincide with the determinant of A. Okay, well, let me also stress that this formula here, indeed you can also recognize this formula probably from the first year linear algebra. This formula is indeed nothing else but the expansion formula. It's an expansion formula along the first row, right? Whenever you study the determinants, you will see that there's this formula, inductive formula to compute them, and that's precisely, it looks like this one. So instead of delta, if you replace delta by the determinant, then this is a so-called cofactor expansion formula for the determinant along the first row. That's it. Okay. Now, right, so let me now state a couple of properties of this function delta that we are going to study. Again, at the very end, we will see that this delta will give us the usual determinant. So we already have seen it. We already have seen it for n equals 2. For n equals 2, because we can. Now, when we wonder what will happen for n equals 3, 4, 5, and so on, right? So we need to get some. We will get some function delta, and we would like to check whether it's actually the determinant that we have been studied already in the first year in algebra. Okay, so in order to do this, let me first prove several facts concerning this function delta. And one of the facts, okay, so one of the facts would be, yeah, so we would like to check the delta, if I apply delta to the, say, to the identity matrix, IN, then what do we get? We must get always 1. So that's for any n. Okay, so well, let me give a proof. Indeed, the proof is pretty straightforward. One just needs to apply this inductive formula, this cofactor expansion formula. Okay, so well, first of all, right, in order to apply this, okay, what we can do, we can just use the induction, right? Because the formula is inductive formula. So use the induction on the n. Okay, so the base of the induction is n equals 1. For n equals 1, what is this formula? How does it look like? Well, it's just a 1 by 1 identity matrix, right? And that's clearly 1. And now if you apply delta to 1, by the very definition of delta, this is the identical function, so it must be 1, so it's okay. Okay. Now assume it holds for, say, for n. Want to check it for the next value for n plus 1. So this is our induction hypothesis. And now, well, we apply this to prove this formula for the next value, which is n plus 1. Okay. So, well, let's look at the delta of in plus 1. Let's look at the delta of in plus 1. And what's this? Well, this is the delta of the following matrix, right? So look, I mean, I just put here the identity matrix. However, what I would like to do, I would like to draw it like this. So it's an identity matrix. It's size n plus 1. However, there's a small identity matrix like this one of the size n sitting inside, right? And well, this is the first row of this matrix, the first row of this matrix. So you see there's a 1 and then all other entries are zeros here. Okay, so now just apply the formula, apply the definition, apply the formula, Well, what's that? The delta of in plus 1 by the very formula, if you see, that's a sum, right? Let me write it. The sum from j from 1 to n plus 1. Just let me just remind you this formula here. So the sum from j from 1 to n plus 1, right? Minus 1 times 1 plus j. Then delta of this matrix in plus 1, and then I remove the first row in the jth column, right, times a1j. Now, what are the a1j's? Well, a1j's, the elements right here. And we see that all of them, except the very first one, are just zeros, right? So indeed, in this sum, the only summand which will survive, which will be non-zero, is the very first one, which would correspond to a11, right? So let me write it. So this is indeed, so only the very first summand which will survive, so it's minus 1, 1 plus 1, delta of in plus 1, 1, 1, tilde, times a11. Again, all other coefficients, all other entries are just zeros because just next ones, right? So, but then look, I mean, what do we have here? Well, minus 1 to the power 2 is 1, right? But then delta of this matrix, well, what is this? Well, this matrix is precisely the small identity matrix. In plus 1, tilde of 1, 1. Because this smaller one is obtained precisely by erasing the first row and the first column, right? Okay, so what do we get? We get just 1 times delta, so this is just delta of what? Of in, right? Again, a11 is just 1. So, but now by the induction hypothesis, look, we assume that this formula holds for n, right? So indeed, delta n is 1. So, well, that's just 1, so that's 1. And this gives us the formula for n plus 1. Now, by the induction, by the mathematical induction, the proof is finished. So this formula is valid for all n. Okay, so that was the first basic property of this function, namely that this is just so whenever you evaluate this function at any identity matrix, you will get 1. The function delta is multilinear, is a multilinear function. Well, in particular, since we are talking, so there's this number n involved because we are talking about, say, n by n matrices, right? It's a function from, say, n by n matrices to the field f. So it makes sense to specify this and call it not just multilinear, but say n linear. So it's n linear function. Okay, so how does the proof works? The proof, so again, I mean, all proofs, indeed most of the proofs, most of the facts concerning the function delta that we defined, they are by induction. Why? Because the function delta itself is defined by induction, right? By inductive formula. So let me do this. So we prove again by induction on n. Okay. And so again, what's the base? The base is clear. The base is just n equals 1. The base is just n equals 1. And in this case, there's nothing to show because we all know that in this case, delta is just the identical function, which is of course one linear. Well, it's indeed just a linear, right? An identity is an example for linear transformation. So that's linear. This is one linear. So the interesting case, of course, so what we need to do is we assume that this property, that this is true, that this is true. So delta is n linear. We assume that delta, or maybe better, yeah, maybe better. Okay, let me do it. So is say not n linear, but say n minus 1 linear is n minus 1 linear. So it's a previous value, and then we want to show that delta is n linear. Again, so this assumption here is the so-called induction hypothesis, and then using this assumption, we would like to deduce that delta is n linear. So n is the next parameter, right? Okay. So okay, so basically what we would like to do, well, okay, so we need to introduce some notation, right? As usual. I mean, okay, so as before, so the matrix A will have coefficients ij, and now, well, suppose that. Okay, so well, suppose that. So okay, let's just pick up the rth row of A. Well, say, so this will be this one, yes, AR1, ARN, and well, suppose that this row we can write as the following. So just some other vectors, say U1, UN, plus some scalar, say K, times V1 to some other vector, Vn, where K is a scalar. Again, why we assume this? Because you remember that whenever we would like to check that something is a linear transformation, right? There are two conditions to verify. First, that it preserves the addition of vectors, and second, that it preserves the scalar multiplication. And at the same time, what one can do, one can also combine these two conditions in one, right? You remember that you just, well, in order to check that C is a linear transformation, it's also enough to check something like this. U plus KV is the same as T of U plus KT of V. So whenever you have any presentation like this, any linear combination U plus K times V, you can always expand it like this. So if this property holds for T, then T is a linear transformation, right? So it's like a combination of these two properties to check. So here we sort of want to apply the same approach. So we want to also, because we want to check that, look, I mean, we want to check that some function is multilinear, right? So what we have to do, we have to check that this is sort of linear with respect to each of the, well, doesn't really matter, with respect to each row, with respect to each column, right? Okay. So, right, so suppose that we pick up a row and then we can write it like this. So then what we can do, well, okay, so let maybe introduce another notation. Let AU, so that's a vector U here, maybe, and that's a vector V. Okay, let AU denote the matrix obtained from A by removing, by replacing the rth row well, simply by, so this is rth row, I just replace it by this vector, by this U. So instead of this vector, I just put this one. Yeah. And well, similarly, let AV, so that's a V, denote the matrix obtained from A, so by replacing the rth row by this one, by the vector V, by V. So just a convenient notation. Now, well, let's just remember this. Then now say if R is 1, if you're just talking about the first row, well then by the formula that we have in hands, we can write that delta A is what? Is j from 1 to m minus 1 to the power 1 plus j, right? The delta of A1j tilde, I just write it down the same formula, A1j. And now we'll look, I mean, let's just look at this matrix. What's that? That's just a matrix obtained from the matrix A, right? By removing the first row and the jth column, right? And what else do we see? Well, we also see that this coefficient, this entry of the matrix A, is just this one, uj plus kvj. Yeah, so here's a j from 1 to m. So we can just substitute it, right? And get the following formula. So delta A equals to the sum from j from 1 to n. Now again, minus 1 to the power 1 plus j. Then delta of A tilde 1j. And then I just substitute. So here I just put uj plus k times vj. And then, well, we can expand it. And, well, just expand this sum. So sum of, so it's a product of this, right? So it's a two sums. So sum from j from 1 to n, minus 1, 1 plus j, delta of A tilde 1j, and then times u1j, u1, yes, u1, okay, u1, and then plus, well, look at this k, you can move it out of the sum, k sum j from 1 to n, yes, minus 1, 1 plus j, delta, still, we just copying it, times now v, v uj, vj. Okay, and what we can do also, we can also write it down as, well, but look, I mean, what is this expression here? Well, this expression is precisely, by the very definition, it's delta, right, of what? Of AU, and this one. Because look, this matrix AU was obtained by taking the matrix A and replacing its first row by the vector U. Okay, then plus, and well, again, and what is this one? What is this sum? Well, this sum is precisely delta of the matrix V, right? So meaning that, look, I mean, what did we check is that whenever we have, I mean, if our R is just 1, so for the first row, so we take its linearity with respect to the first row, then of course delta is a linear function. It's a linear operator, it's linear, so it's a linear transformation, right? So delta is the linear transformation with respect to the first row, Okay, so now, well, what we would like to do, we would like now to show that delta is right. So now we would like to show that delta is a linear transformation, is a linear formula is, well, first of all, it satisfies the following properties. Delta of IN is 1 for all n, right? And second is delta is n linear with respect to the rows, right? With respect to the rows. So, well, this actually, since the, as I mentioned, the usual determinant, if you remember from the first year linear algebra, also satisfy the same cofactor expansion formula. And it also, of course, satisfies this property. It makes sense, we will see it later that indeed it will coincide with the determinant, but I mean, it makes sense to call delta a determinant function. Okay. So, so again, I mean, this was one of the examples of the determinant of the multilinear function, but also, of course, some other examples. So let me now consider other examples of multilinear functions. So other examples or non-examples. So, well, let's look at this one. So let's look at F from again n by n matrices to the field F. And well, let's just look at the following function. So it takes the matrix A, takes any n by n matrix A to the product of its diagonal entries. So it's A11, A22 times, and so on, times A and n. So I claim is that this F is n linear. Why? Well, let's look at what it does with the matrix. So this is my matrix, right? A11, A1n, ANn, AN1. And so basically I'm just looking at the main diagonal, take the product of the values, right? That's what my function does. Now, well, how do we check that it's n linear? Well, just take any row Well, doesn't matter, you can also take column, right? Take any row and take any row, say ith row, so it's I1, AIM, and again represented in this form. It's like U1, UM plus K times V1, VK, VM. Okay, and well, what do we want to check? We want to check that if we apply f to this u, that's my vector u, and that's my vector v, u plus kv, then it's just the same as f of u plus k of f of v, right? Again, we would like to have this property for each row, because it has to be multilinear, right? For each row, not just for one chosen, but for each row. But of course, well, you can just choose the ith one, the general one, and then see what will happen. And then, well, let's just see what's okay. So what will happen with our matrix if we substitute like this, like before, right? Like in the previous proof. So for instance, we have this matrix A11, A1M. Here's ith row AI1, AIN, AN1, ANN, and then we can expand it, right? We can expand it like this, A11, A1N, and then, well, instead of this, we just put U1, UN, AN1, ANN, plus, then K times this, okay, so we can just write it, A11, A1N, right? Then KV1, KVN, AN1, ANN, right? Yes, so we just look, I mean, we just expanded the ith row into the sum. And that's a true operation, just a sum of two matrices like this. Now, well, if I apply the function f, what will happen? Well, I just need to take the product of the diagonal entries, right? And if I apply the function f here, what will happen? Also, I need to take the product of the diagonal entries, right? Okay, so let's write what's the product here. A11, instead of ith factor, I just put ui, and then ANN. And what's the product of the diagonal entries here? It's plus A11. Then I just need to put, instead of the ith factor, I just put K times VI, and then that's just ANN. And it's very easy to see that indeed this is nothing else but just the product of the diagonal entries here, right? So it's A11, ANN. Yes? Because what we can do, we can just put, well, if you wish, more precisely, what we can do, we can just move UI on the left, so just the remaining product here, move this KVI on the left, and then use this formula here. Well, basically, UI is just what? Is just UI plus KVI, right? Using this formula, we get the true identity here. So this just shows that this expression coincides with this one. So the function f is linear with respect to the ith row. But of course, this argument works for any I, for each row. So it means that our function is multilinear. So that's another example of a multilinear function. Okay. So now maybe another non-example of a multilinear function. So non-example. Well, let's look at this one. Say f from where to where? From m of f to f, which is given now. Well, I take a matrix, 1m and 1am, and send it to the, not the product, but the sum of diagonal entries, A11 plus A n. So this is a so-called trace of a matrix A, right? If it's A, then this sum is called the trace of A. Trace of A. Now, what I claim is that the trace is not a multilinear n-linear function.